In this video, we are going to learn how to compute hazard ratio showing effective treatment for two different intervals. Okay? And so this Kaplan-Meier graph showed survival probability of a patient and who are treated with cabbage versus who are treated with medical therapy. And this is a cohort of veterans and who have a stable angina pectoris. Okay? And half are affiliated with cabbage and other half are treated with medical treatment. And as you see, survival by cabbage is better for the first half of the study period. And then cabbage group actually did have worsened survival for the second half of the study period. So if you compute Cox regression change in the effect of cabbage, you will miss the effect of cabbage. So a regular Cox regression and you have hazard ratio of 1.11. So that indicate cabbage increased risk of death by 11%. And which was not statistically significant. So what we did is we really average effect of cabbage over 22 years. And then Kaplan-Meier graph clearly show you can't do that because effect of cabbage is changing over time. So we need to compute hazard ratio separately for first half of follow-up and the second half of follow-up. So that's what we're going to do today. So in SPSS, and there is a Cox time dependent covariate. So this is a regular Cox regression, and today we are going to use this option. And data we have today is a cabbage, and we to look at 22 years survival. So this is a time to death variable survey year, and status indicate 1 for death and 0 for being alive. And treatment indicate 1 for cabbage and 0 for medically treated patient. So we instead of going to Cox regression, and we go to Cox with time dependent covariate. And then first thing we do is we highlight this T underscore and put it in expression box. Then we let SPSS know where you want to cut. So I'm going to cut at 7 years. So you put T underscore greater than 7, right? And then click model. So time variable is survey year and status variable is status, and we called it 1 for death. So put 1 in this box. Through the treatment main effect, so treatment as itself and interaction between T underscore cov underscore. So this is a variable we just created in previous dialog box. So we set T underscore greater than 7. So that's this variable. And then we highlight both treatment and T underscore cov by pushing control button. And then we put the interaction term in covariate box. And this is all we need to do. And then we click OK. Okay. So this is what we have. So exponential beta for treatment is hazard ratio of death by cabbage for the interval before 7 years. So in order to get the hazard ratio of death by cabbage for interval after 7 years, you need to multiply by 0.741 times 1.875. And so let's go to lecture note. Let me repeat again. The exponential beta for treatment is a hazard ratio for death by cabbage before 7 years, and which is statistically significant. So that means up to 7 years. And we saw significant difference by cabbage. Okay, it was significant. And then if you look at interval after 7 years, and you can compute hazard ratio by multiplying 0.741 in 1.875, so which is 1.39. So that's the hazard ratio of death by cabbage for time after 7 years. Okay, and which means hazard ratio for this cross product term is really the ratio between two hazard ratio before and after 7 years. And so if this p-value for cross product term is significant, that indicate effect of cabbage change over time. there is interaction between cabbage effect and time. And another word, we can say effect of cabbage was modified by time. So we can get the hazard ratio for time after 7 years just by multiplying these two numbers, although we can't really compute p-value for the hazard ratio after 7 years. So if you want to compute p-value for the hazard ratio after 7 years, and my suggestion is you can go back and redo this analysis and then set the t underscore instead of using greater than 7 and set it to less than 7. Okay, and then repeat this analysis. Okay, so let me do it again in SPSS. So you go back and survival and go to Cox time dependent covariate, and instead of set t underscore greater than 7, set this to t underscore greater or less than 7. It doesn't matter which, if you put the equal sign for whichever the period. And you click the model and then rerun the analysis. Okay, so now treatment hazard ratio for treatment is capturing hazard ratio after 7 years. So that is 1.39, and it matched with product of 0.741 and 1.875, and now you get p-value, right, 0.003. So based on this, and we can say effect of cabbage, having a cabbage, mortality increased by 39%, and which was significant after 7 years. Okay, so if you put the hazard ratio on this table, you can put it this way. So before 7 years, hazard ratio is 0.741, indicating cabbage reduced risk of dying by 26% compared to medically treated patient, and then p-value is significant. And after 7 years, hazard ratio is 1.39. That indicate cabbage increased risk of dying by 39%, and that was statistically significant. And a p-value for the interaction. Okay, so we can assess whether 0.741 and 1.39 are different or not, statistically different or not, and that is 0.001. Okay. So this is the p-value on the cross-product term from our analysis. And so when you see the effect of treatment changing over time, it is very important to perform analysis separately for the time interval where you see the effect changed.